I hope I'm audible enough,
This call
right?
is now being recorded.
Am I audible
Yes,
enough?
yes, ma'am.
Okay, fine. I hope Ram session would have taken frequency responses, and I've heard that you people have solved few problems on the frequency response. I want to continue with that so that we can start off with a new topic like compensated design in the next class. So, just a warm up before that. I want to write down some important concepts that can be looked down as a notes while preparing for the exam. So, in the frequency responses, so far, before that, we have seen some topics related to time responses. For example, root locus analysis we have done. So, that will help you find the stability of a closed loop system based on the open loop system responses in a time domain manner. But this other two tools that are Bode plot and the Nyquist plot that helps you understand the stability of the system and to visualize how well the system responses changes with respect to the change in frequency using both Nyquist and Bode respectively. So these two techniques are frequency response techniques. Root locus is a response analysis technique. So in Nyquist plot, one of the technique in the frequency responses, we'll start off with Nyquist plot. So what on the whole, like in a nutshell, what Nyquist plot will tell you is stability of a closed loop system using open loop characteristics or open loop system. So this will tell you the stability of a closed loop system with the knowledge of a open loop system alone. So you don't need to determine the closed loop system transfer functions or its characteristic equations or anything. So what do we usually do is if this is our closed loop system, if our closed loop system would look like this, we will determine the stability by finding the pole location of the denominator that is equated to 0, which will be called as characteristic equation. So we will find the poles of the 1 plus g of s into h of s. If those poles lies in the left half of the s plane, then it is stable. If it lies in the right half of the s plane, then it is unstable. This is how we usually do with the time response analysis. Now, in frequency response analysis, what we going to do is instead of g of s, we are going to change this to g of j omega. Only by changing this omega from 0 to infinity, we are going to see how the response of the system changes, and thereby we can infer the stability of the system also. This is another type of technique we used to do if we get to access the frequency response. And when it comes to a real-time system, if you can measure only the frequency response when giving a sinusoidal input, this kind of methods will be useful for you. Right. So how we are going to measure the stability based on the Nyquist plot. So if you see this, instead of finding the response with respect to 1 plus g of s h of s, we are going to consider only the g of s h of s, that is the open loop response. So based on this, if you want to consider this will be centered around -1. So instead of seeing whether the Nyquist plot has contoured around either clockwise or anti-clockwise around the origin, we are going to see with respect to -1. That's why always in the Nyquist plot, we will consider -1 as an origin since we are dealing with only the open loop system, not the closed loop systems. Okay, this is the first point to consider. Don't get confused with -1. Should I consider the contour whether it rotates around -1 or 0? Always, if you use open loop system, you should see whether it is rotating around, revolving around -1 or not. How much it is rotate, how many times it has rotated, and in
Excuse me,
which
ma'am.
direction. Yeah.
That 1 plus GS
times HS was the characteristic equation that you have written, right?
1 plus?
1 plus GS times HFS was the
Uh-huh.
characteristic equation. Okay.
That is the characteristic equation, yeah, for the closed loop system.
Okay, got it.
So if we consider 1 plus g of s into h of s, the evaluation contour of this function of s will enclose the entire RHP containing the zeros and poles of the closed loop system. So we evaluate the contour that encircles the origin. But in case of open loop system, it is just shifted from origin to -1 since we are equating that g into h equal to -1. That's why we are always seeing whether it is encircling -1 instead of 0. So whenever you are using open loop system, whenever you are considering open loop transfer function, the Nyquist plot of those open loop transfer function should be evaluated whether it is encircling around -1 or not and in which direction. Based on the direction, you can say this many poles are in RHP, this many zeros are in RHP. We will come to that in the next step. Okay, this is the first preliminary concept you should you should think. And the next, another hint is for minimum phase system. I hope you are familiar with this. Minimum phase in the sense all poles and zeros of the system lies in the left half of the display, right? So if all the poles and zeros of the system lies in the left half of the display, then the system is called as minimum phase systems. So this is the typical kind of system. What do we call as stable system? So for this kind of systems, how the Nyquist plot will look like, kind of shorthand method. So if you consider this quadrant, like this graph, so for a stable system that has all poles and zeros lies in left half of the S plane. It depends on the where the contour will start and where it ends. Contour. It depends on the type of the system. So for this kind of, for example, for a type 0 system, this is the starting point. This will start in this quadrant, right? For type 1 system, this starts here. For type 2 system, this starts here. This is, I'm telling for only the minimum phase system that has all poles zeros lies in the left half of the S plane. For type 3 system, starts in this quadrant, right? This is the ending point. End I will represent using the green. End of type 1, end of type 2, type 3, and type 4, right? So, for example, if you take a type 1 system, then it starts from here and ends here. Sorry, it's a type 0 system, I'm telling. Starts from here and do some graphical, like some degrees it will take and then ends here. If it is a type 1 system, it starts from here and ends here. Similarly, this is how the Nyquist plot of the system will look like. On the go, you can calculate it. If you see the transfer function of the system, if it is minimum phase, you can just visualize it. This is how it is going to be.
And when you say contour, you mean the minimas or maximas?
I'm meaning the Nyquist plot, Nyquist contour we used to draw, right?
Okay.
I'm
Okay,
telling,
okay.
right. So the overall takeaway from this is change in shape of the Nyquist plot can be predicted due to an addition of pole or zero, right? So when a pole is added, the plot will shift by minus 90 degree. So if I start with a system like this is a type 1 system. For type 1 system, in the quadrant, it will start from here and goes here. My Nyquist plot will move like this, right? So when I add a pole to the system, for example, if I add S plus B, so this Nyquist plot will shift to minus 90 degree. So it will start here and end here. It becomes type 2 system. So when I'm adding keep on adding a pole, it will try to shift to minus 90 degree. Similarly, if I keep on adding a 0, it will shift to or shift by plus 90 degree.
It is somewhat similar with Bode plots.
Yeah, both are similar because both we are measuring using like based on the frequency response analysis. And the way we are doing also same gain margin, phase margin, whenever you are calculating, it will also be similar. But both serves different purposes. That's what it is. So if you see Bode plot, 1 minute. If you see Bode plot, Bode will be visualizing the same system using magnitude and phase plot. But Nyquist plot will give you in a complex plane. And it is evaluated based on the phase margin and gain margin, where the Nyquist being calculated using the encirclement of around the -1 value. And that Bode plot basically will be used to design and tune controllers, for example, PID tuning and all. But Nyquist is more towards analyzing the stability. Okay, so just keep this in mind for different types of system, that is minimum phase system, how where the Nyquist plot will start and where it ends, and if you increase the pole or origin, the type of the system will also increase. So similarly, the shift of the Nyquist plot will be there. So it can be asked for a 1 mark or 2 mark. If this is like intuitive based, concept based questions, not really a math based question. For example, I can show you an example and say if I'm taking a type 0 system. So how we will calculate, instead of S, we will just substitute j omega. So this will be separated into magnitude and phase. Omega square t square, and the phase would be right. Can also be written as tan inverse of omega t. So as how will we evaluate? We will start off with, if we want to draw a contour, we will start off with assuming omega equal to 0. When omega equal to 0 in the quadrant or in the graph, where the Nyquist plot will start. When omega equal to 0, if you substitute 0 here, it will give you 1. Right? Magnitude of g of j omega will give you 1. And if angle would be tan inverse of 0, 0.
Which is
Angle,
45 degrees.
yeah, 45,
Which is 0. Which is 0.
0, right? As omega tends to infinity, we will evaluate if it is infinity, 1 by infinity, it will be 0. Angle would be 90, minus 90 degree, right? So it will start at 1, 0 degree, and it will try to go to infinity at minus 90 degree, right? So it will go similar to this, right?
Yes.
Okay. So it will go to infinity. So this 0, it will be infinity. Right. 0 degrees. Minus 180 degrees. It would be minus 270, minus 90, or other way, if this is 90, this is 270, this is 180 also, when it's being represented using the positive degrees. Right. So from this is type 0 system. So it is started from this end and ends in this end. Similarly, if you try for different types, you will notice this trend. So for type 1 starts from here and ends here. Type 1, it will just shift to minus 90 degrees only. Okay. This is another thing. And then and the next thing I want to share is this Nyquist stability criterion. You are familiar with that Nyquist stability criterion?
Yes, ma'am.
So, Nyquist stability criterion. This will tell you if open loop transfer function g of s, h of s has k poles, some arbitrary value k poles in the right half of the S plane, then g of j omega, h of j omega locus as omega varies from minus infinity to plus infinity. This locus must encircle minus 1 plus j0 k times. So, if a open loop poles present in the right half of the S plane, then there will be a important thing is counterclockwise direction. So there will be a counterclockwise direction encirclement. Okay, there will be a counterclockwise direction encirclement. This is a simple statement, right? So if there are open loop poles in the right half of the X plane, there will be a counterclockwise direction encirclement around the minus 1 in the polar plot. But how many number of open loop poles lies on the RHS will be the number of times this encirclement around the minus 1 in the counterclockwise direction. This is what the Nyquist stability criterion tells you. So if there is a
Ma'am, number
counterclockwise,
of times in the sense?
number of times it will be rotated. Like for example, if this is minus 1, Nyquist plot might look like this.
Okay.
It was not perfect, but something like this. Both will be counterclockwise direction. So encircling around the minus 1 will be 2 times here, right?
Yes, ma'am.
2 times it has encircled. So you can conclude that there are 2 open loop poles in the right half of the S plane. Like if there are 2 open loop holes on the right half of the S plane, then only this will happen.
Okay.
Kind of if and if only if. That's what they are telling. So if there are k poles of the open loop system are in the right half of the S plane, k times the polar plot will be encircling the minus 1 in a counterclockwise direction. Right? This can be easily represented using the formula That is Z is equal to N plus NP, N plus P, where Z is the number of zeros of closed loop system in right of the S plane. Number of zeros of closed loop system. Please pay attention to this line. Number of clockwise encirclement of -1 plus 0j. This is clockwise. And P is the number of poles of open loop system in the right half of the S plane, right? So in the same formula, there are two different things happen. This is number of zeros in the closed loop system, number of clockwise, and number of poles in the open loop system. So what this formula represent is, for example, if I take n plus p, if I consider this, this is number of clockwise circlement, not anti-clockwise. Don't get confused with the stability criterion and this formula. Okay, this is clockwise encirclement, right? This is number of open loop system poles, that is G of S, H of S poles. So if I have two poles in the RHS, open loop systems poles, two poles in the RHS, this is number of clockwise encirclement, 2 times it will be, let's take. 2 times it has encircled the -1. Then this will be added to 4. So 4 poles, 4 zeros of closed loop system are in right half of the S plane. So this represents the system is a non-minimum phase system. It can introduce a delay into the system. So the closed loop zeros are in right half of the S plane. The number of closed loop zeros are 4 number here. So you can just shift this, but you have to be very careful while you are shifting this formula. This can also tell P equal to Z minus N. This is another formula. But when considering this, this is number of open loops poles. This is the anti-clockwise direction. When we are considering this, this should be anti-clockwise direction, and this is same number of closed loop zeros. While shifting the formula, please be careful. Different books have been using the different formulas. I'm also not sure about it right now when I'm writing it here. So you should stick to one single formula and follow that. Okay. You can get the remaining part from the single formula itself. Right. So the next thing is there are few stability analysis and the conclusion of the stability analysis. The first one is if there are no encirclements. If you couldn't see any encirclements around the -1 plus J0, this implies the system is stable if there are no poles of open loop system in the right half of the S plane. I can redefine it easily. How I can say is if the open loop system is stable, meaning the no poles of the open loop system lies in the right half of the S plane. So in my Nyquist plot, if this is this and my Nyquist plot looks like this, for example, there is no encirclement around -1. So here, how I can conclude is my closed loop system is stable provided my open loop system is also stable. Because sometimes the open loop system can have unstable poles, but when you convert it to the closed loop transfer function, it becomes stable. The other way is also possible. When the open loop is stable, closed loop system might be unstable based on the gain value and feedback. So based on this Nyquist stability criterion, one first point how we can conclude it, if you couldn't see any of the encirclement, the closed loop system is stable provided the open loop system is also stable. If the open loop system is unstable, closed loop system is also unstable. Clear?
Yes, ma'am.
Right. The next point is if there are one or more counterclockwise encirclements around -1 plus J0, the system is stable if the number of counterclockwise encirclement is same as the number of poles in the right of the display. Okay, good. So here what they are telling is number of open loop poles in right of the S-plane equal to number of counterclockwise encirclements. Okay, according to the second point, for example, this is -1. So one time it has encircled counterclockwise direction. If my open loop system pole has one pole in the right of the S-plane, for example, S+1 into S-2. One pole is in the right of the S-plane and one is in the left of the S-plane. So the number of encirclement around the -1 in counterclockwise direction is also 1. So if this is same, then you can say the system is stable. For example, if there is another pole that lies in the right of the S-plane, two poles of open loop system are in the right of the S-plane, but only one counterclockwise encirclement happen, then the system is unstable. It will be confusing at first, like how to remember all these things. Just when you try to plot the Nyquist system, and once you properly understand the stability criterion, like fixed with the formula, only one formula, if you can stick with the one formula, you can easily derive all those things from the Nyquist stability criterion formula itself. Third point, these are just byproducts. If you can remember this, it will be easy for you for a 1 mark or 2 mark. Otherwise, some people will have this format, like they can study anything, they can read anything and remember that. Some people will have a practice that they will stick to a formula and derive everything from that during the exams. Both ways it will be helpful for you. Whatever way you can choose that. And the third point is there are one or more clockwise encirclements. Similar to the second point, if there are one or more clockwise encirclement, I'm talking about -1 always, okay? The system is unstable. This is very straightforward point. So if there are one or more clockwise encirclement, then the system is unstable. That's it. When it is counterclockwise, you should see how many poles are in the right of the S-plane in the open loop system. If both the numbers are same, then you can say it is stable, otherwise unstable. But if there are even one or more clockwise direction encirclement around the -1, you can straight away say the system is unstable. Right? There must be the poles of the closed loop system must lie in the right of the S-plane to get the clockwise direction encirclement. Right. So we'll solve one problem and see. G of s equal to 1 by s into 1 plus h into 1 plus s. Right. The first point to do that is both common in root locus and here is identify the poles of G of s for open loop system. So this lies in S is equal to 0, S is equal to 1.
Minus 1 by 2.
Minus 1. So S is equal to minus 1 by 2, right? Now, you know any of the poles lies in the right half of the S plane?
No.
No poles in RHS. Open loop system. So in this formula, where Z is equal to N plus P, number of poles in of open loop system RHS, P equal to 0. Z is equal to N plus P, right? Z is equal to N plus P, where P is the open loop poles in the right half of this plane. If you know the answer now, one of the variable P equal to 0. The rest of the things we are going to find. Okay, in this it will be 0. So this Z should be N for the system which is stable according to the point number 2. If the system is stable, the number of anticlockwise encirclement should be equal to the number of poles in the right half of the S plane, right? Good. There is nothing there. There should not be any encirclement for the system to be stable. Okay. Step 2, evaluating the frequency response. So substitute S is equal to j omega everywhere in the question. So it is g of j omega equal to 1 by j omega into 1 plus j omega into 1 plus 2 j omega. Wherever there is S, I have replaced it with j omega. Step 3, finding magnitude and phase. So this will give me as omega tends to 0. This will become the j omega tends to 0. Wherever there is j omega, it will go to 0. So this will give me what it will give. 0, 1, 1. So the magnitude will be 1. Angle would be, whenever there is a 1 by g of j omega, it will be minus 90 degree. Tan inverse of j omega, tan inverse of 0. Oh, it will be minus, right? Zero minus 90 minus 180. Right? This will be minus 270 degree. Angle would be. Oh, I'm sorry. When is this 0? When you substitute this, it will be minus 90 degree. When as omega tends to infinity, this will become no approximations will be there. Then this one, everything will be taken off. It will be 2 of j omega the whole cube. So the angle would be 0 minus 90 minus 190 degree minus 270 degree. So when omega equal to 0, this is 1 at minus 90 degree. When omega tends to infinity, this becomes 1 by 2 j omega cube at an angle of minus 270 degree. Good. Now we are going to plot the photos.
Omega 10 to 0, how it will minus 90? It should be 0 degree, no?
No, for 1 plus j omega it is. This is 0 degree only. This will be minus tan inverse of j omega, no?
Yeah, but for what is a omega value here? It is a 0?
Tan inverse of infinity.
Okay.
When
Yeah,
omega tends to infinity.
yeah.
Right. Now we will look for some intermediate values to plot the Nyquist plot accurately. I'm taking some in known values like 110.1. So we will evaluate for all these values. Just substitute instead of omega. We are going to substitute this value. So this will become j.1 into 1 plus j.1 to 1 plus j.2. Similarly, when you calculate the tan inverse value, uh, I can easily, I can give a formula so that you can write it easily. And for g of j omega, it is a magnitude. Just use this. It's like writing the complex plane a plus bi equal to a square plus b square root. That's what I have written here. And for angle, this will become minus 90 degree because 1 by j omega always tan inverse of 0. When you are taking an inverse, it will be 90 degree. And tan inverse of omega minus tan inverse of 2 omega. So this is the common formula. So for evaluating the intermediate values, you can use this formula and just substitute the omega value here. When omega equal to minus 0.1, evaluate on this. Just use a calculator and you can get the value. I'm just going to write the value as it is here. If I take 0.1, it would be around by 0.1 root of 0.2 into 1.01 into 1.04. 0.1. Around 10 it will come. Okay. Similarly, for omega equal to 0.5, if I take, it will come around 1.2. When I take omega equal to 1, it will come nearby 1.3 as I have. And for an angle similar to that, if you find 0.1 minus 90 minus 10 so 0.1. 588. This will be nearly Angle would be nearly minus 90 degree. Angle would be nearly minus 170 degree, or 162 degree. So angle would be nearly 200, minus 200 degree. Okay. So now you will know from where, for different values of 0, where it will, for when omega equal to 0, it starts with where it is 1 at minus 90 degree, right? It starts at 1 at minus 90 degree. This is minus 90 degree. Around here it will stop. Right? Then as time goes, for point 1, it is at 10 minus 90 degree. Am I doing any mistake here? This is minus 90. We'll start from here. Not it. We'll start from here. And then go towards here. Right? This is the Nyquist plot of the system we found so far. Okay. Now, if you see, this is where the minus 1 is. It didn't encircle the minus 1 anywhere. So the number of encirclement around the minus 1 region is 0. The open loop pulse is also 0. So 0 plus 0, this will give us 0 in the z is equal to 0. So this is saying that there is no closed loop. 0 lies in the right half of the S plane. So the system is stable. This is how you identify whether the system is stable or unstable based on the encirclements of the Nyquist plot. Okay, and I can give you some intuition based question, or like kind of from content how we can find it.
I'll find sometimes elementary. This week 8, when you're planning to cover?
I didn't understand. Can you come up again?
I mean, week 8, we have assignment on the compensatory design.
Yeah.
So I'm not very sure how to approach this problem because.
Oh, in design
And
assignment you are asking?
yeah. So that's the assignment cutoff date is tomorrow only.
No, it will be like it will be extended because we haven't framed the question. You got the assignment, no, right?
There is a pen and paper assignment in the week 8. Do we need to do that?
Yes,
Or?
ma'am. There is the assignment for the week 8, pen and paper assignment.
Let me check it. I'm not aware of it.
And the
And
deadline is
that's
tomorrow.
One
seems
minute.
like quite difficult questions for us, to me
Yes.
actually.
Yes, ma'am. The questions are quite difficult.
I seriously don't know about it. Let me check with it. I haven't framed that question. Week
And
8, it is there.
what you're asking?
In week 8, it is there.
Yes, you get
Ma'am.
the GA portion.
Design of lag compensator using root locus. That one.
Yes, that's right. So there are 4 questions: mix up MATLAB and pen paper.
Please submit your handwritten answer PDF here. This. Can you tell the question number?
I mean, the first question itself I started and then overshot and not able to judge the poll analytically. So it seems like we need to draw some graph, then find out the poll, and then proceed to find out case. So those are steps. Not sure how do we do it easily.
Oh, this graded assignment. All the questions you are asking.
Yeah, I mean that question, all question. I don't think we have covered it. Yeah.
No, you will. Oh, compensator design. Yeah, it is there. Not we haven't not covered it in the live session, but it
Yeah.
is in the week 8 content. So you want me to cover that compensator design?
Yeah, I mean that will be helpful to us. Yeah, at least not today, but maybe before the assignment closing date, so that we can do that.
Yeah, we can do. No problem. Right. I will go to the compensator design now. And if you have any doubt in this Bode or Nikos, we can discuss it again different time.
Ma'am,
Yeah.
will the week 8 assignment be extended?
The question has not been framed yet. So you will get a design assignment. It is like based on pen and paper and MATLAB based solving. So you should solve it and submit the code for it. You will be given some quite a time to solve those questions.
So the currently which is available, shall we do it or we should not proceed with that?
Yeah, this you have to submit. This is like a common graded assignment. This doesn't have to deal anything with the design assignment. That is separate.
Okay.
This is like all the weeks you are submitting the graded assignment, right? So
Yeah,
since
yeah,
it
yeah.
is a control or design based, this requires some more effort. That's it. But you have to consider this as a regular assignment only.
Okay.
Okay, I'm looking for questions with the compensator design using root locus. Compensation. You studied about PD compensation, PID compensation.
No, only the lead and the leg, I think, and the lead and leg both.
Lead and lag you formed, right?
Yeah.
Okay. It must be there in this book. It's not main. Compensated design using Bode plot have not been covered in week 8, right?
No, that's week 9, I think.
Okay.
And the quiz 2 questions, are you framing or professor only will do?
Professor only. That design assignment we are framing.
Okay.
Professor will check that and confirm it.
No, for the quiz 2, I'm saying.
Quiz to everything, Professor.
Okay. So, any mock he's planning to give us this time?
No mock for anything.
Okay.
And ma'am, quiz 2 will be objective, right?
Yeah, it will be objective.
Okay.
Like always I say, like it will be short answers, will be one line answers. MCQs, MSQs you can expect. Okay, see, in the graded assignment 1, I cannot solve it directly. I can give you the hint. First question A, determine the value of K if 20% overshoot to a step input is desired. So you can
Yeah.
use the 20% overshooter. Okay. Right. In the overshoot example, one minute. Couldn't find any suitable question for this. Wiki. Settling time was given, right? Here.
No, I think the first question there was no settling time.
For
It
the
seems
above
like
A, determine the settling point. Okay.
Ma'am,
Yeah.
can you please clarify once more that the week 8 assignments deadline will be tomorrow or it will be extended?
No. This week 8 assignment deadline will be tomorrow only. I was thinking about the design assignment. That's what I told, that it will be extended.
Oh, okay, ma'am.
This week 8 assignment, it's regular assignment. That's a part of your, like, similar to all other weeks. So its deadline is tomorrow. There is no scope to extend it.
Okay, ma'am.
Mm. Okay. There isn't any questions related to that. Everywhere the settling time is being given. It is easy to find if you have the settling time in your hand.
Yeah, but for I think the lake compensator, they won't be settling time, correct? Or only for lead they give the settling time.
Uh, I'm just finding a similar problem so that I can teach you how can we do that.
Yeah. Do you have a copy of Professor Gopal book? I mean the design control system.
Nagarath and Gopal.
Yeah. Do you have the copy of that?
Yeah, I have.
Can you share with all the students if possible?
Oh, PDF.
PDF, yeah.
No. I have a like physical book.
Physical, okay.
Okay. Okay, compensation will be there with the root locus, right? I will see that. Okay. We can find the exact problem, but I can solve similar problem. We can discuss on that.
Last week task.
What?
You say something? I did not.
Yeah, I have found.
I had a test in Myra and not come.
I couldn't find similar problem. I can solve some problems based on compensator design, and we can discuss on.
Yep, that's will be. I mean, if you solve something order 3 in the numerator, we can
Yeah.
get some idea.
Right.
Yep.
Chapter 5. Right? Okay. Find a compensator for G of S equal to 1 by S into S plus 1. That will give a overshoot of not more than 20%. So its overshoot percentage should be less than 20%. Okay. And rise time should be no more than 0.25 seconds. So it should be less than 0.25 seconds. Okay. So first of all, we have to design a compensator. When you design the compensator, like compensator in the sense, there is a kind of controller. So the difference between these two is like this is, for example, this is a plant you want to control. This is the input, and some feedback would be there. What is this? This is what we are going to design. This controller will give you exact value, like exactly what you want to do. This compensator will try to compensate for the insufficiency. It won't be very exact, but it will take you to the range, satisfying range. This is the minimum satisfying operation I can give. That kind of range it will push the actual system or actual plant. So we have to find this compensator value, or the what pole or any zeros, number of poles, number of zeros we want to add, so that we can compensate for the insufficient desired responses. Right. First of all, you need to find the, this is a second order system, right? System would be a square plus s plus 0. There is no constant here. This is a open loop system. Right. When you try, first of all, we need to find the damping ratio tau. How we will find the zeta? We will first write it in terms of a closed loop system. Then zeta would be 2 zeta omega n is equal to 1. Omega n squared equal to 1. Omega n would also be 1. Then this will become zeta equal to 1 by 2. Right. Excuse me. Okay. Sorry. Right. Now we found zeta equal to 0.5. Right. Now we have to find the k value, so that the system will meet the requirements. This is a very bad example I took because it requires MATLAB cell. This request MATLAB, I couldn't get access to that, so I'm switching to another problem. K by S into S plus 2 into S plus 3. The first question is, what value of K will result in a velocity error constant Kv equal to 10? So they have given a open loop system with a gain K. We don't know the gain, but they are asking for what value of K the overall system's velocity error constants will be 10. So we know this from the steady state error value we found. We can use the same formula here. Limit s tends to 0. Yes, since it is a velocity error constant, there will be yes. We are going to find Kv and the error constants will be 1 by Kv. That will be E of S.
Both planning everything.
That's
They are
60, I
making all
think.
the control.
So this will be S
Both
into S
what
plus
they are
2.
doing.
Can you please
Everything.
mute? Right. So this will give you when S equal to 0, K by 2 into 3 Kv, K equal to Kv is 10 we know into 6. So K equal to 60. So this is the value of K that will give Kv equal to 10. Right. The next question is the closed loop system stable? How can we find it? Using Routh-Hurwitz criterion. So just substitute the K equal to 60 here. S into S plus 2 into S plus 3. This is G. You have to find the C of S by R of S closed loop system. So that will give you 1 by S square, S cube. So S into S square plus 5S plus 6. Right. Now we'll do the route stability criterion. 1, 6, 5, 60. 5, 6, 30 minus 60 divided by 5. Minus 30 by 5 minus 6. Then this will become again 60 straight away. So there is one sign change. So the closed loop system is unstable. Okay. Now we know the closed loop system is unstable. Now we are going to compensate it according to the question. The third question is, what is the gain crossover frequency for the gain adjust system? So the hint is we have to use the K value that was obtained above. They have asked what is the gain crossover frequency for the gain adjusted system. First we need
Excuse me, ma'am.
Yeah.
Ma'am, that minus 6, don't you think it should be minus 30?
No, this will become
Okay,
30
okay. It is.
minus 60
Okay,
by 5.
right.
Right. Now, the question is to find the gain crossover frequency at the gain compensated system. So, the first thing is G of S is, G of S we know, S into S plus 2 into S plus 3. So, gain crossover frequency would be omega GC. So if we find the magnitude of it, this will be equated to 0. So it will be 60 divided by j omega into S plus 2 2 plus j omega into 3 plus j omega. And if I take this will be equal to 1. So instead of omega, I'm going to substitute omega GC since we are trying to find that omega GC. So this will become omega GC square root of 4 plus omega GC square root of 9 plus omega GC square equal to 1, right? So just squaring both sides and taking this to the other side, you will get omega GC square into omega GC square plus 4 to omega GC square plus 9 equal to 3600. So when you try to solve this equation, if you take omega GC square is equal to x, this will be x plus 4 into x plus 9 equal to 3600. X cube or x into x square plus 13x plus 36. So if you find the equation or roots for this equation, you would get three values. Out of it, I'm going to write whatever it is in this range. It will become rest of the things are negative, so we are discarding it. And then omega GC square is equal to 11.4 something, 42. So omega GC square will be root of 11.4. If I calculate it, it will become root of 11.4. Will be similar as like nearly 3.38. Right? This is your gain crossover frequency. Similarly, if I ask phase crossover frequency, you can use phase values to that. The fourth question is being asked, choose alpha of the lead compensator to be 0.1. You know the lead compensator values, right? S plus alpha 1 by S plus 1 by alpha. That for that, they are asking us to consider alpha equal to 0.1. With this choice of alpha, what is omega m at which maximum phase lead is provided by the compensator. Okay. So if you fix alpha equal to 0.1, usually what we used to do is when we find a lead compensator, we will design a lead compensator alpha value so that we will get the desired step response. Here the question is tilted. Like they have given the alpha value. They're asked you to design find the frequency omega n at which the phase is lead, like phase of the lead compensator is maximum. Right? To find this, since we want phase of the lead compensator should be at maximum, alpha should be 0.2, right? To make this, we have to design a omega, right? So we know maximum phase lead occurs at gain crossover frequency, what we found previously. At gain crossover frequency, the magnitude will be 0 decibels. So when there is 2 At 0 decibels, the gain crossover frequency occurs. So we know this. So while using, okay, I think it's Bode based design. Okay, let me do one in a root locus also. Okay, this formula you know in the Bode plot to find the, this is the magnitude criterion, 20 log of g of j omega. Since we have compensator and the system both in the forward path, we are choosing 20 log of gc and g at the same time. So you can just write separately 20 log of gc plus 20 log of g. This is another one positive thing in the frequency response analysis, because when in using time response, the gains will be multiplied. But in frequency response, when while considering a log scale, it will be simply added together. 1 by root alpha plus 20 log of g of j omega. So whatever g of j omega we know, we have, that is while replacing omega equal to omega m. Sorry, nine.
That root alpha, how it is coming there? 1 by root alpha.
When you are writing it in magnitude, this will be right. So it will become omega square. Then this, oh, since it has only omega x square equal to alpha, we are considering root alpha.
This alpha is a ratio, no? For
Yeah,
that
from
is
the lead
0.1.
compensator design.
Okay.
So it will be 1 by alpha. When you are considering the omega square itself, here it is root alpha. So when we are considering the magnitude criterion, it will become 1 by root alpha. See, for constant gain, how will you write? For example, if it is 40 decibels per second, it's 1 by root alpha. Gain value you will write in terms of like this only, right?
Yeah, that's okay. I'm just thinking about that alpha and omega. What is the relation between that? How that relation has been?
So alpha is the gain for the lead compensator.
Okay.
So we are considering the GC here is the lead compensator. So when
Yeah.
writing the frequencies and the gains for the lead compensator, we are using its parameter alpha. For G, we know the actual transfer function they have given here.
Yeah. Can you write the actual function for GC? I mean, what what will be the expression for that? And then where is alpha, so that we can understand? I think alpha in the numerator, correct? In the GC j omega, alpha will be the numerator, and it will be like s plus ZC in the top, and s plus PC in the in the denominator.
When
So
you
is
have
that the expression?
a compensation like this,
Yeah.
then this will be Z will be greater than P for lead, right?
Yeah.
So if I consider S plus Z will be lesser. So this will be right.
Yes.
Hmm.
Yep. In this form, yes, we can write that. Yeah. So if you substitute j omega here, s and j omega, it becomes. So the magnitude of this function will be 1 by under root omega s square plus alpha square.
1 by alpha square by root of, sorry, alpha plus 1 plus 1 for j omega. Wait. This will become omega square plus 1 by alpha square.
Yeah.
This will become omega square plus alpha square.
Yep. With this, it will come bot in the new denominator. It will be.
When omega equal to 0, magnitude is equal to 0. at a particular grain crossover frequency, this will become 1 by alpha square by root of alpha square. So in the considering 1 by alpha,
It's 1 by alpha square. Yeah.
1 by alpha square, okay. Oh.
It is not a root, I think it is a square. No?
Let me recheck it once. One minute. Okay, when I write it in terms of this, if you see, GC, we know that it will be S plus Z plus S plus P. When I write it in terms of omega, so this zero, so frequency will be, I'm considering it as omega Z, and this will become omega P. And alpha here in the lead compensation design, it will be omega Z by omega P. It is related with that. So omega Z can be written as alpha into omega P. Then omega M, the maximum magnitude, that can also be written as omega Z into omega P, root of. This will give us omega Z, alpha omega Z. Oh, sorry. This will be omega P, alpha omega P, right? So this will give us root alpha into omega P. So omega M can be written as root alpha into omega P. So when you write a magnitude criterion for this will give you j omega m in terms of omega m, since because the question has been asked using to find the omega m when considering alpha equal to 1 for what is so that the phase will be maximum. That's why I'm writing in terms of omega m instead of omega. So I can write it like this. Okay, sorry. Instead of this, I am going to write the omega Z in terms of alpha. Keeping the same term above and below. So this will give me when the at the gain crossover frequency, omega n will be equal to alpha into omega p. So substituting omega m here, this will give you same j won't be coming here, right? Just omega m. So alpha omega p into alpha. Again, this is not coming properly. Why? I think I'm making mistake somewhere.
Yep. I think let us continue with that assumption now because
Okay. Okay,
yeah, yeah.
I will try to rewrite this and submit this PDF. Okay.
Yeah, yeah.
Right. Okay. Right. So if it is taking from this step below, this 20 log of 1 by root of alpha plus 20 log of whatever value g we have been considering, omega m root of omega m square plus 4 root of omega m square plus 9 equal to 0. So when I'm taking 2 log there, this side, 2 log, 20 log will get cancelled. So this will be left with omega m root of omega m square plus 4 root of omega m square plus 9 equal to minus 1 by root alpha. Instead of, I'm keeping the 20 log as it is so that I can change the sign and then I can remove it. So taking the log, I can write it as 20 log of root alpha, right? Then I'm removing the log values. It will be easy to calculate. Root alpha. Right. Now this will become, I'm just simplifying it. Total, this will be inverted. So 60 will come here and alpha will also be inverted. So this will become 60 square, 3600, right? If I make any mistakes here, please let me know. I'm substituting the alpha value as 0.1 here. If I substitute 0.1 here, I have to add another 0 here. Okay. Now, similarly, x plus 4 to x plus 9, whatever we did previously, just this value will change. What we got here, x cube plus 13x plus 36x. Similarly, when you find this x will be equal to some this value. When you calculate it, you will get similar to this. Taking a root, root of 28.89. It is similar to 5.3. Right now, this is the maximum frequency omega m value, so that you will get by substituting considering alpha equal to 0.1, you will get the maximum phase. The fourth question is, what is the phase margin of the system? Just use this formula. Since I think you don't have this in this thing. I started this with thinking that this is based on root locus. So I'm leaving it here. We can use another question. Everything here is root locus based on, sorry, body based on. We'll quickly solve this question. Okay. It is desired that the compensated system meets the following criteria, right? The criteria is that kV should be greater than or equal to 6. You have to find the k value so that your kV velocity constant will always be greater than or equal to 6. And the maximum percentage overshoot should be 25.4. So it should be lesser than that. Maximum percentage is 25.4. This is the upper bound. And the settling time they have given with 2% tolerance is 7.46. So the specification on transients lead to dominant poles. SD, we have to find the dominant poles. Okay. First question is, what is the real part of dominant poles? First, you have to find the dominant poles using the given equations or given informations. Then you have to say what is the real part of the dominant poles. The exact question is that. So with this information, we know percentage peak overshoot will deal with only zeta. The settling time will have for 2% tolerance. This is the formula for it. So it involves both zeta and omega n. Settling time we know, peak overshoot we know. So based on this, from this, can we find the zeta? Because zeta we don't know. So this will become 25.4, the maximum is. So this will always be. Can you find this and tell me? Otherwise, it will take long time. Okay, this is giving me zeta equal to 0.4. So calculate it offline and find. I think this is a mistake. This number is some mistake. So I'm not going to spend time here. Just find with the zeta value is 0.4. So settling time we know zeta omega n. So from this we can find omega n. This will be 7.46. It was given here. 7.46 yes. And this is 4 by zeta. We found it is 0.4 into omega n. The omega n will be here 0.4 into 7.46. So this will give me 4 divided by 0.4 into 7.46. Right. So omega n is giving me around 1.34 radians per second. So omega n are found. So dominant poles can be found using the formula minus omega n plus or minus zeta omega n. Is d equal to minus zeta omega n plus or minus j omega n into root of 1 minus zeta square. Right, this will be minus 0.4 into 1.34 plus or minus j 1.34 root of 1 minus 0.4 square. 0.4 into 1.34 is giving me 0.535 plus or minus j 1 minus 0.16 root of into 1.34. Right, this is giving me 1.34. Okay, these are your dominant pole pairs. So one pole lies on minus 0.5 plus or minus J 1.23. Another lies in minus 0.5 plus, this is plus, and this is minus J 1.23, right? Okay. These are the two dominant pole pairs, and the real part of this dominant pole pair is minus 0.5. That answers the question. And the C question is, this is where the actual compensator design comes. If only a gain adjustment gives the desired transient performance, what should be the K? So you're asking if only gain adjustment, I can adjust only the gain to get the desired transient performance. What then? How can I find the K value? The gain K should be adjusted such that the closed loop poles of the systems are at the dominant poles, so that you will get this desired response based on the transient responses. That's what the hint behind this question is. You found the dominant poles here, right? Just you have to make sure that the poles lies in the dominant pole location so that you will get the desired transient performance. So we are going to use the magnitude criteria of the root locus. So what is the magnitude condition? So when you have GC and G, you will multiply it, right? Similarly, I'm going to write the dominant poles location and replacing it with the original closed loop systems. What is that? Pole location. So wherever there are S, you are going to replace it with the SD. That's it. So when I try to expand it, you know the SD, right? Just substitute it here. Otherwise, it will be difficult. One by K value is 0.5 minus 0.5 J 1.23, right? So this will be K into minus 0.5 plus J 1.23 plus or minus. Oh, since it is a 1.465, when you put plus 2, it will become 1.46 plus J 1.23. There is no change in the phase. Plus 3, this will give you 2.46 plus there is no change in the phase, equal to 1. So yes, it is equated to G of S into H of S equal to 1. Okay, this will become K by 0.5 plus J 1.23, 46 plus 1.23, 2.46 plus J 1.23 will be equal to 1. K by if you calculate this, 1.23 square will give you 1.51 minus 0.25 plus 1.51 1.26 into 1. The overall will be K is similar to 0.04, 7.04. Right? This is the K value. When you, for this value of K, when you keep your closed loop poles at your desired pole location, it will be in the desired pole location. Then your transient response will be equal to the desired response. Like transient response will behave properly, it will give a proper output according to the information given in the question. C question is, what is the velocity error constant KV for the K we obtained above? When K equal to 7.04, what is KV? That you know easily, right? Just do this. Limit S tends to 0. We have solved many problems in this. Put G of S there. Limit S tends to infinity. Sorry, 0. K by S into S plus 2 into S plus 3. That's it. When S tends to 0, this S will get cancelled. 7.04 by 2 into 3. This will give you some value nearer to 1.1. Maybe 5, I think. Not sure about it. Similar to 1.1516 it will go. Right. Now they are asking what is the value of beta assuming we do a lag compensator design. Both lead and lag will be same, but to differentiate it, we are using alpha and beta. But variable doesn't matter. You should know whether the pole will be farther than 0 or the 0 will be farther than pole for lead or lag compensator. You should be clear in that. So they're saying the question tells assume that we are designing a lag compensator, so that what is the value of beta to achieve KV. So KV you found here, right? With the K we found KV. Now with the using this KV value, we are going to find the beta value. Here one thing you have to note is, like, this is a consecutive type of questions. If you make any small mistakes in the calculation in the previous steps, the entire steps will be gone. Entire marks will be gone. You cannot retrieve it. So you should be careful while calculating each and every steps. So we know KV equal to 1.15 and the desired value. Sorry. To achieve the desired value, not the above value, desired KV. Desired KV, it was given as what it was? Greater than or equal to 6, right? So this is actual KV. We got KV is 1.15 around, but the desired KV should be greater than 6. So you should make a compensated design so that you can push the KV from 1.15 to greater than 6. That's how we are going to design a compensator, so that we will get the beta value such that the KV value will be greater than 6. Right? Beta is very simple. From since we know the compensated value, the actual and the desired, we can just use it as a ratio. So this is the desired divided by actual. It's a beta is a ratio of desired versus actual. If you don't know the KV, then this will be a indirect problem to solve it. You have to find the time constant, and from the formula you have to find the beta. Since we are dealing with KV in each and every steps, we can just take it as a ratio. So we know this is 6 divided by 1.15. So this will give you around 5.112 or something. So this is your lag compensator designs or lag compensators beta value. And this is E, right? Okay. With the 0 of the lag compensator at minus 0.1, what is the location of poles of the compensator? So we are assuming we are using lag compensator only. They told that if the 0 is in minus 0.1, to give this desired response when beta equal to 5.11 and the desired response kV greater than 0, settling time overshoot 25.54, and for all this criteria to be satisfied and also the 0 is at minus 0.1, what would be the pole of the system? That's what they have asked. So Z is equal to minus 0.1. So we know the ratios again can be in terms of poles and zeros. This is beta will be 0 divided by pole because it will be beta into pole, right? Sorry, pole B, right? So it is the ratio of this. We know the beta value, just right away substituting it. Sorry, P. So P equal to minus 0.1 divided by 5.1. This will be 0.1 by 5.11 will be minus 0.02. It's a very less value. Since the 0 value is also less in a lag compensator, 0 will be farther than pole. So pole is at 0.02, where 0 is at 0.1 minus. Everything is in the left hand side of the axis. Right. We can discuss more on the lag lead compensator design. I was not ready with the problem, so it took some time. I can come up with some problems, like practical problems for quizzes and also for the exam. Just we will focus on the compensator design for root locus for now before the quiz. Then we can do based on the Bode plot. Actually, Bode is easy compared to root locus, at least for me. Okay, we can wind up the session, I think, if you don't have any doubt.
Ma'am, I'm having one question.
Yeah.
In graded assignment 7, question 1.
Graded assignment 7.
Yes, sir.
Okay. What is the question?
Question 1.
Okay. Okay. Seven graded. It's loading. Consider the Nyquist plot, that question.
Yes, ma'am.
Uh-huh. In 1 and 2, assume the open loop transfer function of the feedback system is having no RHS poles. Okay. Then
Ma'am, before solving, I want to ask one thing.
Uh-huh.
Like in a lecture, sir said that whenever we have a pole, we make a anti-clockwise turn,
Mhm.
and for a 0, we make a clockwise turn.
Okay.
So in the second figure, like it is given in question that there are no poles on the right-hand side.
Mhm.
How is there an anti-clockwise turn around -1 when there are no poles
Right.
in the second figure?
See, Z is equal to N plus P, right? Where this is the closed loop 0, this is the open loop poles. In your first example, if you take,
Ma'am, sir told us it's, N is Z minus P. So,
anyway, either way you can consider. Right, mathematically
yes,
also N is equal to Z minus P, right? That is fine. We will
I think it was P minus Z, sir said.
N is equal to Z minus P only, it will come.
Lecture, but I think it was P minus Z.
Okay, I will see whether it is a mistake or something. But let me do from our point of view, whatever we have learned so far, you see whether it is okay for you. right? Whether it is answering your question. Otherwise, we can discuss that also. Right, in the first question, if you see, it has encircled the -1 one time clockwise direction. Sorry,
Yes.
one time clockwise direction and one time anti-clockwise direction. So the overall big circle also.
In first figure, there are two clockwise turns.
Around -0.1 you see one inner circle circling around clockwise. Outer circle is also clockwise. Okay, right. So two clockwise direction it was there. Right? Am I right? Okay.
Yes, ma'am.
For second system, it is circling the -1 one time counterclockwise, one time clockwise.
Yes.
Right. According to this formula, Z is equal to n plus p. They say assume that open loop transfer function is having no RHS pole. So p will always be 0. So Z is equal to n, whatever case it is. So in the first sum, n is equal to 2. In our case, this is the number of encirclement, clockwise encirclement. Right. In this case, it is 0. There is no clockwise encirclement. In the second case, one clockwise encirclement is there. So according to that, this statement, if there are one or more counterclockwise encirclement, or sorry, the third case, if there are one or more clockwise encirclement, the system is unstable. Right. So based on that, this should be unstable. The second system should be unstable.
Yes, ma'am.
But there is another counterclockwise encirclement that nullifies it. So according to this clockwise and anti-clockwise means there is one pole and one zero at the same location that compensate each other, and it is nullifying the effect. So this considered to be 0 only. So the system is stable. The second system is stable here. If there is only one clockwise encirclement, then the system is unstable. There is another counterclockwise is there, so it nullifies it. So the system is stable. Is it clear now?
Ma'am, one question.
Yeah.
Like the magnitude is different for both the circles. So how can we say that 0 and pole are on the same location?
Oh, okay. Might not be in the same location, but the effect is being compensated with one poles in the one zeros. That's why the magnitude of the circle is different. It is
Ma'am,
not.
earlier we studied that if even one pole comes, like here, that is 0, that will go to unstable. So how is it being nullified if even one is coming, even 1 0 is coming?
No,
That will become pole.
I'm not saying it is in the right of the plane. Then if it is in the right of the plane only, you have to worry about it, right? This is the open loop systems poles and zeros. Even if the open loop poles and zeros are in the right of the S-plane, closed loop system poles and zeros can be in the left half of the S-plane based on the gain tuning and parameters, and also the location of poles and zeros. That's how we are. So this encirclements is of open loops. We are telling about the closed loop system. So even
Yes.
in the open loop system, one pole is in the right of this plane and one zero is in the left of this plane. Since it is nullifying the effect based on the Nyquist plot, we are telling closed loop system is stable. That's the essence of the Nyquist plot. With only open loop, how we can identify how the closed loop system is. Clear or still?
Okay, that
hard
part
to-
is clear. Just
Yes.
one more thing, like it is given that there are no right-hand side poles of
Ha,
open loop. Then
ha.
how can we get anti-clockwise in second figure? How can we get that done when there are no poles? Because for poles, anti-clockwise circles are there.
Because of for poles anti-clockwise circles are there, you are telling there is no poles. That's why the compensation is there. No, this is a kind of reverse question. You please don't think in that way that There is no open, like only if there is a open loophole, then only there will be anti-clockwise direction. That you will come from the, for example, if you are given with the system G of S, okay, when you try to find the Nyquist plot, you will consider the entire system. And there will be two more poles, there will be two more zeros that will push the system towards the right. Right, or it might be marginally stable, even though it has S minus of or S plus or minus 2 j omega kind of systems can be there. So Nyquist plot can be interpreted in that way when you are coming from transfer function to Nyquist plot. But this is, we don't know any aware of the system. Just using the plot, how we can come to a conclusion. So for this, you will these kind of steps will be helpful for you. Just keep these points in mind. And the one formula, stick on to one formula. If you are following the PPT, just go with that formula. If you are following a book, just stick to that formula. Right? So from figure, if you want to interpret it, this kind of points will be helpful for you. Just look into this. How many anti-clockwise rotations are there? How many clockwise rotations are there? Based on that, you will come to a conclusion. Because if the pole, one pole is here, another 10 is very far from them, maybe 100 times, it might not have any influence in the pole. So the root locus can be like this. If it is located too far, the root locus can be like this. So you cannot say it has rotated, so there is no poles, how it is rotated. It is based on the location of poles and zeros also. Right? You are not audible to me. I don't understand.
So ma'am, like mainly you are saying that when we are going from like omega plane to transfer function, so right, so anti-clockwise turn can come.
Yeah, use this formula. Like, don't get confused with the regular thing. Like, if there is no poles, how can it is circling? Just with the given information, with the known points and the formula, how you can interpret whether it is having, it might have be stable or not stable. Just start off with this formula. If you have any doubt, just start off with this formula and then look for the points. If there are no encirclement, first point, whether see how many encirclements happen in -1. So based on that, you interpret it. If there is no encirclement, see whether the question has the open loop poles or not. In this question, they have given according to point 1, open loop pole is no open loop pole, right? So if there is no open loop pole, and if the system is given, whether you know if the system is stable or unstable, then you can come to a conclusion whether the closed loop closed loop system is stable or not. So here, there is no RHS poles, so the system is inherently stable, and there is no encirclement here also. So Nyquist plot gives, overall Nyquist plot gives the information about the closed loop system.
Yes.
Based on the open loop poles, you draw the Nyquist plot. Not really related. Both of it not really related, right?
Yes.
So this gives the information about closed loop system. Until you know what the open loop system is exactly, you cannot come to this conclusion.
Yes.
Okay, then we'll wind up. It's already 7:50.
Thank you.
Thank you.
Yeah, we can solve some compensated based question on Wednesday.
Yes.